Welcome to the Introduction to Measurements presentation. This presentation will focus on a discussion of significant figures. In particular, we will talk about how to take significant figures into account when making measurements and when performing calculations. First off, let's start by talking about two vocabulary words related to measurement. Accuracy is how close a measurement is to the actual value. Another way of saying this is that accuracy is how correct a measurement is, how close it is to our accepted value. Precision, on the other hand, is how close a set of measurements are to each other, or how consistent the group of measurements is. It's possible for a set of data to be precise but not be accurate. For example, I could perform an experiment consistently wrong, and all of my data might follow a certain trend, might be very consistent with each other, but my data still might not be accurate. I didn't get the correct answer that I was supposed to get. Let's talk about different types of numbers. When we talk about digits that are certain, we're talking about things that are known exactly. So for example, a measurement of the amount of money in your bank account, that is a certain number. The bank knows down to the penny how much money is in that account. It's not an estimated value at all. Anything that can be counted will always be considered a certain number. Compare that to uncertain numbers. These are anything that is measured or approximated, anything estimated. So for example, if I measure the height of a person, or if I use a scale to find the weight of a person, these are uncertain numbers. I mean, think about weight. Every time I go to the doctor, I always go, oh, their scale is wrong. You know, that scale says that I weigh more than I do. My scale at home in my bathroom tells me something different. So there is a little bit of uncertainty associated with the measurement of weight because I had to use a piece of equipment to get that measurement. How do I know whether that piece of equipment is calibrated correctly? What if there is some user error in how I read the piece of equipment? So anything measured will always be considered an uncertain number. Well, that brings us into this topic of significant figures. When you write down a measurement during a science experiment, you don't want to basically overstate your measurement. You would not want to write down a measurement to many decimal places. Because when you write a measurement to many decimal places, someone is going to assume that you know that measurement for sure, down to that degree of accuracy. And you wouldn't want to overstate your case if you really weren't sure about that number, if you were really estimating it. So in chemistry, we have a concept called significant figures. With significant figures, you always write down those numbers in a measurement that you know for certain, plus one uncertain digit that is estimated. So as a little bit of explanation with this, when we think about measuring someone's height, I might measure the height of a man using a tape measure, and I might say, oh, this man is 5 feet 10 inches tall. But I would not be very likely to say, this man is 5 feet and 10.13456 inches tall. I can't use a tape measure and measure height out to 5 decimal places of an inch. That would not be a very good way of expressing that particular measurement. So there are some rules about how you take significant figures into account and how you make sure that when you report measurements, you are only reporting what you know to be true, and you are not leading someone to believe that you know these numbers to a certain degree of accuracy if that is not the case. I do want to mention that there are some numbers in science that are considered exact numbers, and these are typically constants. And in terms of significant figures, we would say that a constant had an infinite number of significant figures. For example, you might have heard of constants for gravity. An object falls at 9.8 meters per second squared. You might have heard of the speed of light. Light travels at 3.00 times 10 to the 8 meters per second. These constants are considered to have infinite significant figures, So if I was using such a constant in a calculation, the constant would not have an effect on the number of sig figs in my final answer. So the first thing we want to do is we want to figure out, okay, if I'm looking at a number, how many significant figures are there in my number? So here are some rules to help you determine how many sig figs there are. The first rule says that any number other than 0 is considered significant. So in the number 96,485, those digits are all non-zero digits. There are 5 digits in the number, so there are 5 sig figs in the number 96,485. In number 2, if I have a 0 that is basically sandwiched in between two other numbers, then that 0 gets to count as a sig fig. So for example, the number 101,325 would have 6 sig figs. The 0 sandwiched in between the ones does count as a sig fig. Rule number 3, all final zeros to the right of the decimal place and to the right of a significant figure are significant. So I've got 2 examples to help me illustrate this. The first one is the number 0.0500. Now in this number there are 2 leading zeros, and they do not count as significant figures. But the zeros at the end do count as significant figures. Remember that the rule is that for a 0 at the end to be a sig fig, it must be to the right of a decimal and to the right of another sig fig. So the 500 at the end, all of those numbers are sig figs, so there are 3 sig figs there. Also, another example would be the number in scientific notation. We could have 1.00 times 10 to the 3rd power. That number would have 3 sig figs, 1.00, 3 sig figs there. The 1 obviously is a non-zero digit, so it is considered significant. The zeros at the end are to the right of a sig fig and to the right of a decimal, so they count as sig figs. Rule number 4 says that leading zeros, or zeros that act as placeholders, I call those trailing zeros, that they are not significant. So as a few examples, 0.0821. That particular number has 3 sig figs in it. The zeros at the beginning are leading zeros. They do not count as sig figs. Only the 821 part is the sig fig part. The number 1,000, those zeros at the end, they are trailing zeros acting as placeholders. So the number 1,000 is only accurate to the thousandths place of accuracy, and there is 1 sig fig in the number 1,000. Now, to give you a special case, the number 1,000 with a decimal, that number would actually have 4 sig figs in it. The decimal is put at the end of that number to tell someone that we are sure of those digits to the ones place of accuracy. So therefore, the number 1,000 decimal would have 4 sig figs. Rule 5 says that when you write a number in scientific notation, the times 10 raised to a power, that part of the scientific notation is not going to be significant. So if I have 6.02 times 10 raised to the 23rd power, the only significant part is the 6.02. There are 3 sig figs there, so this whole number in scientific notation is only 3 sig figs. Remember that if you are debating how many sig figs a number has, you can always convert that number into scientific notation, and that way it'll help you remember, oh yeah, the times 10 raised to a power part, that is not significant. So it'll help you figure out how to get rid of zeros that are not significant zeros. Let's look at some examples. All of these on the screen have 1 significant figure. So 7 obviously is only 1 digit, so 1 sig fig. The number 40, the 0 at the end is trailing. 0.5, the 0 at the beginning is leading. 0.00003, the zeros at the beginning are leading. 7 times 10 to the 5th, we don't look at the 10 to the 5th part. We only look at the 7, so 1 sig fig there. And 7 million, zeros at the end, are trailing. How many sig figs are in these numbers? The number 1.2 has 2 sig figs. The number 56.76 has 4 sig figs. In the number 4.00, there are 3 sig figs there. The zeros at the end are to the right of a decimal and to the right of a sig fig, so they do count. 0.0792, that number has 3 sig figs. The zeros at the beginning are only leading zeros. And the number 7 billion, 83 million, that has 4 sig figs. The 7083. All of those 6 zeros to the right, those are trailing zeros. They do not count as sig figs. I'll leave this slide up for a second. You can pause it and you can look and make sure that you understand where we're getting the answers to these particular questions. Let's move into talking about calculations with sig figs. There is one rule when you are adding and subtracting. There is a different rule when you are multiplying and dividing. The rule for adding and subtracting says that your final answer can have no more places after the decimal than the least of the measured numbers. So what we're trying to say is you will round off your answer from adding and subtracting to the least accurate decimal place. In terms of rounding, you will follow the same rules that you would typically use in a math class. You look back 1 digit behind of the place that you want to round to. If the digit behind is less than 5, you drop it. If the digit behind is greater than 5, you round up by 1. As an example, 2.45 plus 1.2 gives us the final answer 3.65 on the calculator. But the number 1.2 is only to the first decimal place. So therefore our answer needs rounded off to the first decimal place. So we are rounding that 6. We look back at the 5 behind it. The 5 tells us to round up, so our final answer is 3.7. Another example, 7.432 plus 2. The calculator gives us the answer 9.432, but the number 2 is only accurate to the 1's place of accuracy. So therefore our answer cannot have any decimal places, and our answer must be rounded to the 1's place of accuracy. So I want to round it off with the 9, but I look back to the 4, less than 5 there, so we are rounding down. The rule for multiplying and dividing. When you are multiplying and dividing, the result can have no more significant figures than the least reliable measurement. So you are rounding your final answer off to the least number of sig figs. Here's an example. The final answer we get on the calculator is 139.111, but the number 2.45 only had 3 sig figs. So we need to round our answer off to 3 sig figs, so we would round that to 139. Here's another example. We have an answer of 727.68, but the number 9.6 only had 2 sig figs. So our answer can only have 2 sig figs. We need to round that answer off to 730 because in that number, the 0 at the end is not a sig fig. So the 7 and the 3 are our only sig figs there. Lastly, remember that when you are recording a measurement, you always report the answer that you know to be true and you add one uncertain digit. So for example, I would read this measurement as the arrow is 4.75 centimeters long. I know the 4 and the 7 because I can clearly see that this arrow is somewhere between 4.7 and 4.8. So I am adding the 5 as my uncertain digit.